Hello everyone, welcome back to my channel. Today we are diving deep into the fascinating world of Linux permission. This is an essential topic for anyone working with Linux or Unix-like system. So let's jump right in. Our key objectives for this videos are fundamentals of Linux permission, demystifying the meaning of files in Linux, explore Linux speeds and permission, and introduce you to key commands. So without further ado, let's set sail on this Linux journey.
First off, let's start with the basics. Every file and directory in your Linux system is assigned three types of owner permissions: user, group, and others. These permissions determine who can read, write, or execute a file. When we say read, it means the file can be opened and viewed. Write allows you to modify or delete the file, and execute makes the file runnable as a program. First, let's talk about what permissions are. In the world of Linux, permissions are rules associated with files and directories that determine who can access them and what they can do with them. Who refers to the user, and what they can do refers to the operations like reading, writing, and executing. This might sound a bit complicated right now, but don't worry, we will break it down. Now, you must be asking yourself, why are permissions important? Well, they provide a basic level of security. They control who can access the files and directories on your system and what they can do with them. For example, you wouldn't want just anyone to modify or delete your important system files, would you? That's where permissions come in.
Now let's dive deeper. In Linux, there are three types of permissions you can set for a file or directory. First is read. This permission determines who can read or view the contents of a file. When it comes to a directory, read permission means you can list the contents of the directory. Second is write. This permission allows the user to modify the contents of a file. If a directory has a write permission, it means you can add, remove, or rename files stored in that directory. Third is execute. The execute permission determines whether a user can run file as a program. For directories, execute permission allows you to access and run the files within the directory. File permissions are displayed in terminal when you list the contents using the command ls-l. Here is an example of a file permission. In this example, the first character dash indicates this is a regular file. A directory would have a D. The next three characters RWX are the file owner permissions, which means the owner can read, write, and execute this file. The next three characters R-X are the group permission, which means the user in the files group can read and execute but not write. The last three characters R-X are other permission, which means user not in files group can read and execute but not write. This is symbolic mode of representation. There is another mode which is called numeric mode. The numeric equivalent of RWXR-XR-X is 755. This system is based on binary and octal representation, where R is equal to 4, W is equal to 2, and X is equal to 1. So for example, RWX, read, write, execute would be 4 plus 2 plus 1 is equal to 7. You can change the permission of a file or directory using chmod command and the owner and group permission using chown or chgroup commands respectively.
In Linux, everything is considered a file. This includes not just text files, images, and directories, but also hardware devices, processes, and network sockets. This approach simplifies the way different entities are handled and manipulated in the system. Let's break it down the three primary types. First is regular files. These are the most common and contain data such as text, program binaries, and data. They can be read, written, and executed. Second is directories. These are containers that hold files and directories. They are also treated as files. The only difference is the D at the start of the permission string when you run the command ls-l. Third is special files. Devices, processes, and network sockets are represented as special files. For example, in the /dev directory, each device is represented as a file. This includes your hard drive, keyboard, mouse, and other peripherals. The idea of everything being a file simplifies input and output operation. For example, to read from a device, you can use the same system calls as reading data from a regular file. This philosophy is central to the flexibility of power of Linux system because it provides a consistent way to handle different resources. Files, directories, and devices can all be manipulated in similar way, which makes the scripting and automation more straightforward. For example, the command cat space dev input mouse 0 could potentially output the raw data of your first mouse, just as cat space my file.txt would output the text in that file. Or echo hello world dev tty1 could write that string to your first terminal. Linux permissions are represented as bits. In Linux, there are few fundamental commands for Linux permissions. Here we'll look at some of them. The first one is ls-l. So let's take a look at that. So currently I am in a directory called home tnh test. Let's go back and type here ls-l, and you can find that currently I am in the directory called home tnh, and in that directory there is another directory called test, and that's why the permission will start with D. So that basically means it's a directory, and the permissions for this are rwx r-x. So that basically means the tnh user and the tnh group here is having read write execute permission, and whoever is not part of the tnh group will have only read and execute permission, but not the write permission in this specific folder. Let's go into the folder and type again here ls-l, and here you can find that there are two files currently in this directory. One is myfilesowner.txt and the other one is tnh_file.txt. The difference in both files are the first files was user and the group both are root, but for the second file the user is tnh and the group is root. And in terms of file permissions also, you can find that on the first file only read write permission are there for the user, and for group and others will have only read permission. But in the second file you can find here that the user is having read write permission, even the group is also having read write permission, but the others user will have the read permission. In our list, the next command is chmod. This command changes the permission of a file or a directory. It can be used in two modes, symbolic and numeric. In symbolic mode, you use U for user, G for group, O for others, and A for all. You also use plus sign to add the permissions, negative sign for remove permissions, and equal to sign to set a permission. For example, chmod space U plus X myfile.txt adds execution permission for the user on myfile.txt. In numeric mode, you use numbers to represent permissions, such as 4 for read, 2 for write, and 1 for execute. For example, chmod 644 myfile.txt sets read and write permission for the user, and read permission for group and others on myfile.txt. So let's try hands-on for the chmod command. So currently I am here in my directory called home test, and if I type ls-l command here, you can find there are two files, file_1.txt and file_2.txt, and both files are having read write permission for current user and read permission for group and others as well. So let's say try chmod on the first file. I want to change current user's permission and I want to add execute permission for the current user. So let's type u plus x and then the file name file_1.txt, and again type ls-l, and here you can find that the current user right now is having read write execute permission. Same try with the numeric mode. So for numeric I'll try 744 and then the file name, again type ls-l, and now you can find that the second file is also having right now read write execute permission for the current user and read permission for group and others. Let's try chmod command for the group. So I want to change the group permission and I want to add execute permission for the group on file 1. Let's type that here, again type ls-l, and now you can find that the current user is having read write execute, but the group permission also changed from only from read to read and execution. So that's the chmod with group in symbolic mode. Now try that same part with the numeric mode. So for numeric mode, I'll also do the 7 7 5 and 4 file2.txt. If I type again here ls-l, now you can find that on the second file also the current user is having read write execute permission. The group is changed from read to read and execution, and the other is having only read permission. So that's chmod for you. You can like use multiple combinations with that for group, others, and all, and with numeric or symbolic, whichever way you prefer. The next command is chown. This command changes the owner of a file or a directory. For example, chown new user myfile.txt changes the owner of myfile.txt to the new user. So let's try that command here. So if I type here ls space l, you can find that there are two files. The first file owner, the user or owner user is root, and for the second one is tnh. So let's try ch own and then change the user to root for the second file, and type again here ls-l, and you can find that for the second file, previously the owner was tnh, but now the owner changed from tnh to root. That you can do with chown command. The next command is chgrp. This command changes the group of a file or a directory. For example, change group new group myfile.txt changes the group of myfile.txt to new group. So let's try that command here. If I type here ls-l, you can find that on the first file the group is root, and for the second file the group is tnh group. Now I want to change the second file's group from tnh group to root. So I'll type chgrp root and then the file name. If I type again here -l, you can find that now the second file's group is changed from tnh group to root. Beyond the basic permissions, there are three special types of permission that you can set in the Linux: the set user ID, the set group ID, and sticky bit. SUID and SGID allow a user to run an executable with the permission of the executable's owner or group. The sticky bit on the other side, when applied on a directory, restrict the deletion of files in that directory to their owners, the directory owner, or the root user. In addition to the basic read, write, and execute permission, there are additional bits of information that affect how the operating system treats the files and directories. The first one is set user ID, SUID. If the SUID bit is set on a file, users who run that file gain the same permission as the user who owns that file. Think of a public library where there are many books. Anyone can read the books, but only the librarian has the permission to stamp or issue the books. Similarly, in Linux, certain commands or programs must be run with higher privileges. For instance, the passwd command, which changes a user password, needs to access system files that regular user cannot modify. With SUID bit set, when passwd command is run, it temporarily gets the permission of the owner to make the necessary changes. When the SUID bit is set, it is represented with an small s owner's execute spot in the permission string. If the file does not have execute permission for the owner, it represented with an capital S. Let's try hands-on on the SUID bit related command. But before that, let's check out the file permission for the passwd. So here I am typing ls-l on passwd binary, and here you can see that currently the execution bit of the current user for passwd binary is S. That means the sticky bit has been set for the passwd binary. But how we can do that on our own files? So let's try that with this command. ls-l, if I do here, you can find that both files are having read-write execution permission for the current user, and I want to set the SUID bit set for the first file using the symbolic mode. So for that I'll use chmod u plus s and the file name, my file, and I'll type again here ls-l, and you can find that the SUID bit has been set for the first file. The same way we can use the numeric mode as well. Instead of u plus s, I'll just use the 4 and then the normal permission. So only difference in the numeric mode is you have to add extra bit 4 in the start of the permissions. So here I'm adding 4 for the SUID bit to set, and then continue with the existing permission, which is 7555, and I'll type the file name here. If I type ls-l, you can find on the both file the SUID bit has been set, and the execution bit for current user for that specific file has been changed from X to S. The next is set group ID, SGID. This is similar to SUID but applies to the group owner of a file. Let's say in an office you have a shared printer. Anybody can send a print job, but the print job needs to belong to a group that manages the printer for them to be printed. So if a user sends a print job, the job will run with the permission of the printer group, not the user's group. In Linux, when SGID bit is set on a directory, any file created within this directory will have its group set to the directory's group, not the user's group. This can be useful in collaborative environment. When the SGID bit is set, it is represented with an small s in the group's execute spot in the permission string. If the file does not have execute permission for the group, it is represented with an capital S. Now let's try the hands-on for the SGID bit. But before typing SGID related command, let's type ls-l, and here you can see that my current directory test is not having the SGID bit has been set here. If you want to set a bit for SGID, type chmod g plus s and then the directory name, and again type here ls-l, and you can find that the x bit of group for the test directory has been changed from x to s. So that basically means the SGID bit has been set. And the same you can do with the numeric mode as well. Instead of typing g plus s, you need to type 2755. So here 2 basically notifies before 758 that you want to set SGID bit for this specific directory, where the user will have the read write execution permission and the group and other will have the read and execution permission. Again check here, and here you can check that the directory permission has been changed from rx to the rs, and the execution bit is set to s. So that basically means test is having SGID bit set. The next special permission bit is sticky bit. If the sticky bit is set on a directory, only the owner of a file in that directory can rename or delete the file. Without the sticky bit, any user with write and execute permissions for that directory can rename or delete the files. Think of a public notice board where anyone can put up a notice, but you can only remove your own notice, not others. In Linux, when sticky bit is set on a directory, any user can create a file in that directory, but they can only delete their own files, not others' files. This is common in directories like /tmp, which is used by many different users and processes, and you don't want one user deleting others' temporary files. When the sticky bit is set, it is represented with the small t at the others execute spot in the permission string. If the file does not have execute permission for, it is represented with a capital T. Now let's try hands-on on the sticky bit. So before that, let's type ls-l, and you can find that here for the others on this directory test, it's r-x. So I want to set the sticky bit for this directory. So I'll type chmod o plus t, and then the directory name. Enter here, type ls-l correct again, and you'll find that the current permission for the test directory in the others section is r-t. So the execution bit for in the permission string for the test directory is changed from x to t. It's because now we have set the sticky bit. So anyone who creates any file in this folder or this directory can delete their own file or rename their own file. They cannot delete or rename others' file created in this specific directory. It's because the sticky bit has been set. The same way, if you want to set sticky bit using the numeric mode, you need to add 1 before your permissions. So 1755 and then the test directory, enter, and now type again ls-l, and you can check that the bit has been set for the test directory to t. So that's the difference. You just need to add 1 in front of your permission. That's a wrap for today. Thank you for watching this. If you found this video helpful, please give it a thumbs up, share, and don't forget to subscribe for more technology tips and tricks. Until next time, keep learning, keep growing. This is the next hacker for you.